Yeah. This is specific to the situation. All right, so we'll continue this lab for everybody else. But here's what I want to do now. Let's imagine that we have an overflow and we know nothing about this. Okay? We have a program. We don't know what these header structures are necessarily, and we don't know why it's doing what it's doing, and we don't know how to control it, right? Let's look at the disassembler, and I'm gonna delete this, and we're gonna start from scratch. Don't save my database. Reopen. Video 9 now. So let me do that. All right, what's the address here that we're crashing at? 0804.
These are requests.
Yeah.
CS367. Oh, it is. That's the one I'm pressing. Yeah, I think that's right though.
Yeah, that's right. That's where you should be.
Oh,
Okay.
okay.
So we've got this assembly here. We know we're in int free. So we've got that symbol, right? So here's where int free starts. Boom. And we got this symbol. And we've got a crash right here. So if you've crashed here, you're already pretty advanced. Generally what's going to happen is you're going to crash at that other place, which is where? Probably the... Where are people crashing? There's a -8 in here that's looking for the previous size that people crash on when they are hitting the size without knowing what it is. Is it this one? No, that's a low effective address. Somebody had a crash here that was from smacking the size. Ah, here it is right here. Okay. So that's generally where you are crashing. Let's look at this function a little bit differently. Right? Let's do something I almost never do and put it into block mode. So if we're crashing here, what we kind of know is, all right, something I did made ECX -8 be an invalid pointer. Okay? What is that? What did I do that made that invalid? Now we know, let's say we know we have a heap overflow. We know we've overflowed some structure, and that makes us crash right here. And so something that we did is making ECX incorrect. So we need to figure out where ECX comes from, and ECX does not live in this block. ECX comes from another block above us, right? It's not in this spot. We're going to walk up and we're going to map. We know what we sent. Let's say we put A's here, right? 4, 1, 4, 1, 4, 1. We're going to say, all right, we controlled that. That made it look at a bad address. Well, let's not do that. Let's make it look at a good address so it doesn't crash there and see what we get, okay? So the first thing that we're going to do is identify the fact that we're controlling a size by looking at that assembly. And we're going to say, all right, if we're controlling a size, it's going to do subtraction to get another pointer. And we know we control all this data. We just put A's here. Let's see if we can make that pointer point inside the data we control. That's step 1, right? We don't know what this thing is doing, but we can say, let's see where we can go if we can get control of what that pointer points to instead of crashing where we are. And that's fairly simple to do, right? And so if we come up with any number for previous size that's smaller than the number that it is, it's going to point inside here. So let's say we picked our 10, and we're just going to use this because we can see that there are no offsets in this function if we just quickly scan it. there are no offsets to this, whatever this structure is, that are greater than C. So 16 bytes is going to give us control of the whole thing. So we set our 10 here knowing nothing about this, okay? And now we're going to get another crash. So somebody who could quickly modify their script, or who has just done this, please write an exploit, or I'll just do it, I guess. All right, so that's it. We got our seg fault. Where did we seg fault? Let's take a look. All right, so just by making that one change and not by having anything else line up properly, we've already end up crashing in the consolidation, right? And I control both of those pointers, right? So straight off the bat, just by bypassing the first crash, which is the size check, or not the size check, but it's making the calculation of where my previous chunk is. If I can make that one calculation, not knowing anything else, point in here, I can already see I've got to write what where. If I see one register being put into where another register points, and I control both of those things, I've got to write what where. Okay? Even if I just controlled ECX in that situation, I instantly know, oh, I control a target, I can write over something. Right? Does that make sense? And that's knowing nothing about what this thing is doing. Okay? And so I could then walk on through blindly, and the problem here is if I do this, it's going to look like something very dirty, like one of yours did. But so that's going to be chunklen minus eight, and then I'm going to have to put something else in there. So we'll do struct.pack. Two of them. One, two. Okay, so still knowing nothing about this, we change this so that it's pointing back inside of ourselves. We know that that pointer is here, and we're looking at plus C and plus 8. And so I'm just going to write something for plus C and plus 8 and see if I can get control of the thing, okay? So totally blind, except not really. Okay, so now I've got a rate what where that I control. Here's the problem. Even with the rate what where that I control, I screwed up a whole lot of stuff. And not understanding what's going on, I've got to get out of this function without it crashing. And it's a complicated function, right? And we assume we know nothing about it. So there are two ways we can go about it. One is we can try to understand what's going on, first level of understanding, right? I can say, I'm going to go do some research on allocators. And in this case, that's very simple to do. It's open source code, and I can understand, I can read papers about this type of allocator, no problem, right? If we're going that way, then what we would want to do here is turn this disassembly into something that's understandable. So let's go that route first, and then once we've gone that route, we'll go the other route, doing it with no understanding, okay? So let's get to our next crash. We say we got our rate, what, where. And I'm actually going to switch back to my other line so we're not getting too confused about what's what here. We've got, let's make sure that one still actually gives us a crash that we expect. Yeah, okay, so we are consolidating that fake chunk just like we expect. And so what we've got is our right, what, where. Our what in this case is EAX, which is our previous, and our where is ECX minus C, which is our next, 43, 43, 43, right? So prev is what, next is where. Okay? So let's decide where we're gonna write here. In this case, I made that fake V table, so we'll have a what is equal to something, a where is equal to something, and we are gonna have to, actually we don't have to pack any of those, because it's gonna pack for us. So our what is gonna be, let's look at our where first. The obnoxious V table that I built is at a hard-coded address, and that address is 08041010. That's going to be the target we're going to write to. We can imagine it's somewhat like a global offset table, or if it's a V table, we have a peak somewhere, right? So don't worry about this section. What I want to actually show is the right, what, where, and how it looks. And then we're going to focus on getting out of free. I expect we'll have another crash. So let's just write 41, 42, 43, 44, which is going to give us a crash in main when the V table is actually used. If we actually get there, that's going to be our next crash we're aiming for, but I believe we're going to get another crash along the way to deal with. So, yeah. Still crashing there. Did I not write this? I didn't write this. Oh, yes. So I wrote a right, what, where, and I didn't change them. So this is our what. This is our where, is that correct? Okay, now we're crashing someplace else, right? That is not where we were before. So we did not actually get our right.
I think you
there.
swapped it.
Did I?
Swapped the ECF.
Let's find out. We're at
Because EAX is
C657. Let's not guess. C657, we're crashing here, okay? Where is our backwards consolidate? What is that address, our backwards consolidate address? Right here. So we're crashing before we ever get there, or we're crashing on a different free, okay? So,
no, you just
That's not
swapped.
backwards consolidate.
say what?
I don't think that's backwards.
It's not, right? You think they're backwards? Yeah, that's possible.
No, it's just the what and the where is swapped. Maybe. Let's see.
No, isn't it, there needs to be like an offset, right?
like plus C or something.
Oh yeah, you're right. There we go. Where is our? It's going to be minus OXC. But that's
Oh,
not
is it?
actually the problem. That's just still be writable. It doesn't matter, right? Alright, so that'll do. Should still crash. Yeah, there we go. It's gonna crash on the top chunk.
Speed, you good?
Alright. So, X. 60. Yeah, okay, so we got our right what where. No problem. But we're still crashing inside int free, right? So my target here is my vtable, and I wrote a different vtable position to it. So the two functions that are loaded in this program are free and system. So free is at offset actually 50 and offset 70. I am an assembly programmer. When I wrote this, I was like, I want this at offset plus 10 and plus 20. But because vtable is of type int, when you add 10, you're actually adding 10 times 4 in C, not so in assembly, but in C there's types, I guess. So, but that's just why it works out that way. So even past, once you've changed those two pointers to right where you want, and you got that right, you're still stuck inside your free. Okay, so let's imagine that we know this is the allocator and we can start looking at it. Even though we don't have the exact code, we're going to use the malloc code that's very similar. Oops, no, over here. We're going to use this malloc code. The free is at, if you want to follow along, 2287, line 2287, okay? So we know this is what it looks like, and it does a couple of things if we scan through it very quickly. It checks to see, what does it take for arguments? It takes our pointer, it checks to see if our pointer is 0, then it does mem to chunk. I happen to know mem to chunk is take the pointer and subtract 8. It's just a macro, right? So we're going to look for that in there. That's one thing we can anchor on. Then we're going to have, I know we have this nmap section, and this is actually inlined. So if we are to go to look at mmap chunk, whatever code is there is going to be in our allocator. But let's start like this. Let's actually use the decompiler, and I'm going to do a couple things to make this nice for us to read. So I'm going to line the two up, and I'm going to say synchronize, which means that if I select a line over here, it's going to show me the assembly, and if I select the assembly, it's going to show me where it thinks that decompilation is, okay? The other thing that I did to make this a little bit nicer on this screen, if you are going to use IDA, is I went to general here. This instruction indentation is usually 16, which is kind of obnoxious because it pushes everything over and unnecessary. So in order to get it to fit and make it nice and readable, I make it something very low, like 2, and now I can kind of see everything, right? So let's go to the top of this function and start working our way down. First thing we note is that there's actually 2 arguments here, not 1. So one of these is going to be our pointer, and one of them is going to be something else, and we don't know what that is, right? So this is slightly different. That's number 1. So which one of these is likely to be our pointer? It says A2 is a D word. Let's change that. Let's make it take byte, is that gonna work for you, or let's just make it char? No?
Can it be voiced out?
There we go, okay. So the reason I want it to be char star is the same reason that I screwed up my C in terms of numbers. I want to see this in terms of actual bytes. I don't want to see it bytes times whatever size it is. So I make it a char star, it's 1 byte. Okay, so I see A2 minus 8, V2 here. So what's likely going on there? If I've got pointer that's an argument minus 8, that's probably what? It's probably the chunk, right? Okay, so I'm going to rename it first off. A2 chunk to free. Okay? And so now V2 is going to be of type chunk header, right? So when you are doing reverse engineering, whether you know what's going on or not, you are going to want to be building structures for everything. So let's imagine for a second we don't know exactly what this is. We're going to look at V2 here, and we're going to say, it still thinks it's a D word. Let's make that into a char star. No, it does think it's a char star. What the heck? Oh, it's cast a D word. I'm sorry. Okay. So I still think it's an int, so that's 8. So I've got plus 8. I've got plus C. Here's a plus C and a plus 8. Do I see anything that's larger than a plus C on that? And the answer is no. Running through here, I see everything being either C or less. So to start, we'll say view, subviews, structures, local types. There's it. And we're going to make a new type. We'll call that, because we know it's called malloc-chunk, we'll call it malloc-chunk. And we'll give it a bunch of entries. So I want a bunch of integers. We'll start there. If it turns out that this size is actually larger than that, then we'll add some more, basically. But we've seen this much, so we'll start there, okay? We're going to go back here. Oh, not there, here. And we're going to go back to the top, and we're going to say V2 is convert to struct, all the way at the bottom, malloc-chunk. Okay? So V2 is our malloc-chunk now. So okay? So we've got, here's the first use of A1, and it seems to be a rather large array that a bunch of more complicated stuff is looking at. If you have the source, especially to the other version, and you kind of understand how this thing works, then it's very easy for you to kind of say, because a lot of the code is dependent on whether a size, we know this is a size because I can see it being masked, right? Anytime it does these guys here, check in use, and with a prev in use, all that stuff, those are all masks. So you see this not prev in use, I'm gonna say that this guy here is our size. It's also -4, right? So our chunk here, -4 is the my size, right? So that's a size, call it my size. Okay, this is our masked size. And then we see that the size is being checked against some number that keeps coming from this A1 array, right? Everything that has to do with that A1 array is being checked against the size, and sometimes We do a little calculation based on the size plus some fixed length, and we put that there. Now, my guess is that those are the bins, okay? So like if we were looking at malinfo, is that where it is? Yeah. Which we looked at previously. Right, we've got that, and then we've got also somewhere in here there's just a pile of bins. Let's find it so we can see what it looks like. No, these are all the macros. Well, we don't actually know where the bins are, because I'm not going to go searching for them. But because we understand that the look-aside lists are a set of size-based bins, we can kind of guess that A1 has something to do with that, right? It's some array that's storing a bunch of sizes. So even not knowing that, let's call it size-based array. We don't have to know its bins, we'll just call it size-based array, okay? We never seem to go in here. Every time we call the program, we don't seem to go in there. And it's looking at my size and 2. So what's my size and 2? We're checking a bit in the size. There's a number of flags. 1 is in use, we know that, right? There's also 2 and 3. Ah, there we go, there's 2, is M mapped, okay? Going back to our free function, we see one of the first checks here is M mapped. And then a bunch of stuff happens in M unmapped chunk. Here though, no function is called except for unmapped. So let's go to M unmapped chunk and take a look at what it's doing. There's a bunch of assertions which are probably not going to be compiled in because we're compiled not in debug mode. So those assertions are probably going to be gone. But I see 2 things. First thing here is I only have 2 local variables, size and ref. But I do see this, nmaps and nmapped mem. And those are likely globals because they're not locals here, right? So they're going to be someplace else in the program. If I look over here inside this thing, I see the same basic structure. I see some global is getting decremented, some global is being minus my size, right? Or pre-size. So I can label those globals and mmaps, and I can label this one, what is it? mmapped underscore mem. Okay, so that's not necessary because we're never going in there. We're never going to work on anything in this block because munmap is going to call whatever that pointer is, and there's not a lot we can do to make that useful to us. It's going to ask the kernel unmap something. If we give it a bad pointer, it's just going to crash. Okay, and we're never going in there. We're not going to set anything, set our flags to 2. Okay, so then what happens immediately after our back to free and say what happens after this block, this nmap block. Well, the first thing is a check for in use chunk, and then it does a bunch of other mapping. It says our size is going to be equal to whatever that header is, and removing the prev in use, so that removes the flag. It's going to find our next chunk by using the my size with this macro, chunk at offset macro, and it's going to get the next size from next, so it finds the next chunk and it gets its my size. Okay, so let's go back and look at our assembly and say, all right, what do we got here? Chunk to free plus my size is gonna be the next one. So this is
Next one.
our next chunk. So first off, let's change this type. Set type, oops, not like that. We're gonna cast it to a struct. Convert to struct, malloc chunk. And this one is going to be also a malloc chunk. Okay, so this is next chunk. Okay, and then we've got yield 4 plus mass size. So that's we're not quite certain, but this is another unmasked size, right? So we're moving the in use bit, and in here we're checking the previous in use bit for 0. So go back out here and we say, where's the next time that it checks the in-use bit for 0? It was right here, right? So my size and previous in-use bit not, so if it's 0, run this block. And it's got this nice lovely comment that says consolidate backward, right? And in here, we've got a pretty good idea of what all of the elements to our object are. So let's say, first thing that happens is this is our prev size. Yeah. One of the things that's kind of obnoxious about working with a disassembly, especially in cases where there are pointers that start in the middle of a structure, is that you can't really necessarily cast them perfectly. And so you have situations where in an ideal world, we'd be able to cast that to a structure and automatically kind of see what that is. But because we're looking in the middle of a structure, it doesn't work out very well. Now there are, in newer versions of IDA, ways to actually do that. They're extremely obnoxious, and I'm not sure if Hydra has them or which disassemblers do or do not allow for it. Yeah, so it's something to be aware of and something that actually looks a lot nicer inside assembly. All right, so
Wait, what is the type of chunk?
it's
The middle of that.
It's the middle of it.
Yeah,
That's
okay,
why
that
you're
makes
seeing
sense.
that
Yeah.
problem, right? And then it also decides it's going to cast a D word every time we do that. Let's put this to malloc chunk. That's a little bit nicer. And chunk to free. It's prev size. That's also malloc chunk. And yield 8 is going to be.
Does it have 8?
No,
Yeah.
but it's field plus 8. Right?
Oh, I see.
So that's our forward pointer. And C is our back pointer. Now we actually have the structure for this, so we could just go through here and name these my size, prev size, right?
Wait, isn't the previous side?
Right, right.
Okay.
And this guy is also of that type. And so,
Oh.
right, as you're doing this, and you are creating structures and defining them, now everything becomes super clear, right? So this is a back chunk. That's our forward chunk. Because everything uses structures, if you define your structures properly and cast everything, it goes from being utter nonsense to being, you know, basically perfectly readable, right? And then we can go back up now and say, my size plus my size is equal to our next chunk, right? It's gonna be our next. Yeah. But we now know this is the place where we got our right will where, right? At C654, It's forward back is equal to back forward is equal to forward. It's the same basic on-link strategy, and that's what it looks like in assembly, right? There's your EAX is moved into ECX plus C, and likewise here. Now, our next problem, now that we've gone through all of that, is that we're still crashing in the thing, right? And the question is, where are we crashing and why are we crashing there? So we want to get out of here kind of safely, right? So we are crashing at C67E. So let's go to C67E, try to figure out what's going on. Where are we in our source? Okay. So we are at another consolidate. Call that F2 and BK2. And both of these are, of course, struct. Okay, so here's our back consolidate. And then here is yet another consolidate. So what other consolidate comes next in the source code? If we go back and look at the source code now, here's our backwards consolidate. Here's some nonsense after our back consolidate. That actually tells us quite a bit. Right? This is all right here. So set head, top, threshold. If we wanted to go and fill in this whole function, we could do that, right? We could say, oops, we could look through malloc trim and set head. This is probably a macro if I had to guess, and this is probably a function or an inline one. And this would coordinate with that code. We could name all this stuff, right? But what we're really looking at is, okay, we crashed here. So what exactly is that, right? That's gonna be, that's gonna probably be either this guy here or this guy here, right? They're both the same structure. They're both unlinks. So how are we getting there and why are we getting there? It's not exactly obvious. There's two ways to go about it. One is we continue on this path trying to figure it out. The other one is we do it like this. We say where we had gotten our unlink is so this is where we want it to be at C654. So let's set a breakpoint at C654. C654, and then where we actually crash is C670. C670. So let's set our brakes. Brakes are C654. And then we'll set another one at C67E. And we're going to try to figure out, with dynamic analysis, exactly why we ended up there where we don't really want to. And if we can get around it. So C654, okay. P. Displow, German. Okay, so in this case, we're going to see our what and our where, right? So info reg. There's our what and our where. So ECX is our where. We add C to that, it's 1010. We're trying to write 1060 at that, right? So we're going to step. And if I now look at 08, 04, 1010, it should say 1060. So we got our right where, we're good. Where did we go wrong is the question, right? So there's our reciprocal right. That's no problem. That doesn't crash. EBP minus 10, which is going to be, from local is going to go to EDX, and we're going to compare it against EDI plus 54. So what's EDI plus 54? EDI plus 54.
Could be the global.
Yeah. want to go in here. That's not going to do us any good. And we are going here and we don't want to be in here. So this is the thing that we do want. What's that exactly doing? It's checking next chunk my size plus 41. What's 41? We didn't label that. And 1. So what do we kind of think is going on here, seeing that and not equal 0?
Like if that base set, right?
Yeah. Which bit is that?
Previous.
In use, right? So it's checking to see if some other chunk is in use. So it's going to be looking in some direction. And since we've done the previous, that's probably the next consolidate. So it's probably going to be looking up here to see if this one is in use or not. Now, this is not a complicated program and doesn't necessarily require a lot of protection, but let's think about, we've screwed up all these numbers, right? If the thing is free, or if it is in use and somebody calls free on it, that's gonna check all these headers, right? So how can we make a situation where it's not going to do that necessarily? Well, one thing we can do is say, oh, you know what? All the chunks around me, those are in use chunks. And no one will ever free them because they're not actually in use chunks, right? And so they'll never come back to the allocator. And so, in our current situation, what have we smacked? We've got, probably smacked my size with something too, right? We smacked that whole header. So, it's going on to consolidate other things thinking they're free. And so it's going to be incumbent upon us to figure out what it's checking to see if it's free, and then go set that to be in use so that it's not trying to consolidate it again, right?
The next chunk being used for
Yeah, so we know it's looking there. This is the check that we want to pass. That check is here, and here's where it's getting it. So let's set our break at C666. C666, the check break. No, that's for the other debugger, thank you.
If only.
If only that existed.
No, only with the debugger.
Oh.
We're at C660, which is the check immediately previous to that. And let's see if we pass it or not. What's it actually checking? We're at 660. If I step, we get to C666. Okay, so EBP minus 14 is going to move into EDC X. Let's see what that is. X P minus 14. That's 0. Where's it getting that from? Where did it get EBP minus 14 from? Right? That's our question.
Which local is that?
Hmm?
Which local is that?
Which local?
The EVP minus.
That's a good question. Minus 14, right? So, here's our check. One is a size. Let's mask my size. So it's probably next chunk. So CX, and then it's going to do a bunch of math and check it. So what's EDX? EDX. Also 0. But it's coming from 08A64BO. And info A64BO is here. And what is that?
Is that heat?
That's our heat. All right, so let's say that next chunk is probably what we're looking at because it's on the heat and it's looking at a my size, right? So where exactly is that relative to our other chunks? Now we could go back and run it again and set a breakpoint earlier on and figure out where exactly is pbuff1, where exactly is our fake chunk, and where exactly is pbuff2. But you can also be dirty about it. You could just be like, EDX minus. Search around a little bit and figure out what we're looking at here.
So you're trying to get the top of the heap.
Say what?
Are you trying to print out the heap?
Yeah.
Just do the info proc mapping. It'll give you the top address of the heap.
Well, so, okay, so if I do that, I know in this program that I'm gonna be close to the top of the heap because there's only 2 allocations. In a normal program, if we were doing this, we would not know where we are in the heap, so I could print the whole heap and try to find those, right?
It'll give you the lowest address on the heap though.
Yeah, but also that's not gonna necessarily be anywhere near where we are, right? So, I mean, we can print out the whole heap, right?
Dump the whole thing.
Right.
Are you saying like in a situation where there's a ton of chunks and you?
Yeah, right, like, so in that case, you wouldn't wanna dump the whole heap out, you'd wanna say, well, EDX is relative to where I was, what is it likely to be relative by? Well, it's likely to be, like, OX 108 away from us, right? Like, that's likely to be pretty close. Ah, there it is, okay, cool, right? Like, because I know the chunks are 108 size, I can think relatively and say, okay, what am I looking at here? What I'm looking at is the chunk that comes after my fake chunk. Why do I know that? Well, I see that 41414242, right? And I know when I wrote my script, my chunk, my chunk looks like this.
Is there a way to like 2-column format it so you can kind of like see the?
Wait, isn't this the 4142, the fake chunk? Or am I wrong?
No, you're right.
Okay.
Right? So here's where we are. This is our 414141424242. So where we are looking minus 108 is pbuff2. So what we're looking at is the chunk after pbuff2. Now that is all zeros. It hasn't been used. So what we need to do is set ourselves up another chunk here and say, don't worry, you don't have to consolidate me with the next chunk I'm in use, right?
Wait, why isn't the top chunk also having revenue set? Because isn't it allocated?
We are not pointing at the top chunk necessarily,
Why
right?
not the top chunk literally, but like the lowest address chunk?
The problem is that the size is coming out as 0, so there's no entry there. It should never, oh, okay. So it is keeping track of the top chunk, and for some reason it's not checking it. But not understanding that, what we can do is add ourselves a top chunk. Like add another fake chunk and say that it is in use. Right, so then you could do this a couple ways. I could set my size to be 10 and then put this top chunk here. I'm not gonna do that because it all happens to be 0. We'll make a chunk size amount of data, and then we will put up here another fake chunk that is in use so that it won't reconsolidate us. So that's
Why is it
something
trying
like
to
that.
consolidate above though?
Say what?
Why is it trying to consolidate with the one that already exists? Because that one hasn't been freed yet, right?
There is no other one above pbuff2, so it is always, your top chunk's always a free chunk, right? So
Wait,
let's
are you doing
say
the forward or the backward one?
we did previous, so this is the back. We get the overwrite from the previous consolidation, and then it checks the top chunk. And so if it says, oh, the next one is the top chunk, we always want to consolidate with the top
Oh, this
chunk.
is low down.
Yeah, so we are looking at the end of the heap that's unused, right? So now it's like, oh, I'll just put all this together, and then if it's big enough, I can free it back to the
I
output.
was looking at it from low to high this way.
Yeah, no,
Because we checked
I wrote it that way for the stack, right? Okay, so what's happening is, we've got this consolidation, now we're getting this consolidation and we don't want it. So let's make it not happen. And the way we're gonna make it not happen is we're gonna say, we'll overwrite this header too, and we'll make it say it's in use. And so it won't try to do that consolidation, right?
So you had it and you're leaving.
Yeah. So what I do is, I fill up the space from here to here,
Yeah.
and then I put sizes in there that say, this previous one, that one's in use,
Yeah.
don't consolidate it, right? So, we make another chunk. I've added now our chunk length is C, and then another top chunk, and the top chunk looks like this. It's got another size of chunk len, it's in use, this is nonsense, doesn't matter,
Yeah.
but I don't wanna make another pack header, so I'm gonna put it there anyway, it's not gonna get used, right? And then we'll go back and try it with the top chunk, but with all of these breakpoints set, so we can see that what we think is right is right. Which one is this? Is that pre two? Can't see. Oh, it's okay, so.
Left arrow.
All right, so
That's the right over there.
that's our right what where. Flow reg, EAX and ECX, there's our right what where. Okay, we're gonna continue. Here's our check for ECX, so step I, and say info reg. Okay. ECX and EDX are now, EDX is now a legitimate heap pointer, right? Whereas before it was 0 and we were crashing there. And we're gonna check that size, so like if we say X, EDX, and we'll give it the whole 4X so we can see our whole header. Our
Previous size.
previous in use is set. Here's our two other pointers, right?
Yeah.
Wait, don't you need to set the chunks like size itself too?
It's not gonna matter. So here's the
There's no
thing.
check on that?
Here's the thing. If we want everything to be correct, we could do that, but we don't necessarily need it to be the case. What we need it to be the case is that it satisfies enough checks to return without crashing, right? And no one else will make use of that. And that's kind of the point of what you're doing when you don't understand what a complex function is doing. You're not looking to get it correct, you're looking to satisfy all the checks. So if this works and we don't crash anywhere else, then we've satisfied everything and we're pretty good to go, right? So let's step through it. We don't crash, are we gonna jump there? Nope. Yeah,
No, we
so we
didn't.
do. So we jump over that block. We're not gonna do the consolidation, which was at 7-4, right? So we went around that block. Let's continue and see what happens. We get back into main and our regular where has worked. So the point here is you can understand it, and if you understand it, what you should be doing is creating structures and mapping them and gaining that understanding. Or you can understand the checks and how they relate to your data that is being input and just simply work around them, okay? And it is advantageous to mix those two things up to go quickly through a complex situation. If you understand, then you map it. If not, and it's not necessary, you can simply get away from the checks that you don't want to have occur, right? And because your data is controlling how that flow works, all you really have to do is say, okay, I'm crashing in this block. I can do one of two things. Can I exercise the bug while I also change this data to not crash in that block? Or can I just avoid the block, right? And so a lot of that is, here's my crash, walk back to find out where the branch is. What's the branch checking? Oh, it's checking an in-use bit. What in-use bit is it checking? Oh, it's checking the one that is the next chunk from where I am. Okay, so I put something there that bypasses that check and I walk on through. Make sense? This is not like an easy thing to go through in an hour. So I apologize if I was going back and forth a little bit quickly, but does any of that make sense to anybody?
No, I get it.
You get it? Some people get it.
I somewhat get it.
Here are the things to understand. You don't necessarily have to understand what the program was intended to do, merely what it's doing based on your data. If you do understand what it's doing, that can help you get through that situation more quickly, and so you should try to combine those two things. As you are looking at what data decides which way a branch goes, because you gave it the data, that can tell you what the structure is, so you can then start labeling structures to make it quicker, right? But basically what you are trying to do is avoid the situations where you don't want to crash after you get what you're done what you're done, and get out safely, and that's it. You control that stuff.
You ever compile, like if you're working in a new allocator, you compile an open source allocator, you ever compile the allocator of these debugging symbols and then link the binary you're trying to exploit against the debugging symbol allocator so you can see where you're crashing in the allocator? Like source code, so using that as the source code.
No. But not for any good reason. I'll tell you the two reasons I don't do that. One is, for the most part, I worked in Windows, so there was never source. But two, when I did work in Linux, I was never attacking the allocator, right? So I was never looking at the actual allocator structures.
Is that a workflow though that you would suggest? Like,
Yes.
if you have an open source?
I would suggest that if you have open source and you know exactly what version and exactly what compilation flags, or you can figure them out, then yes. The problem that you're gonna have is, okay, I gotta go and compile this on the right version of GCC with the exact flags that they use to distribute this thing, and they're probably gonna be related to the make file, but the config that I use is gonna be, you know, a big deal there, and trying to line that stuff up is good. So what I would do is this instead, is I would compile my own, and then I would bin diff the two and port the symbols over. And then I would use the original one with the compiled symbols. Which is not usually how Linux people work, but if you have full type information and you have all the symbols, your disassembler is gonna do a really good job for you, right? Like, this here now is pretty darn close to what the source looks like, right? Like, this is pretty darn readable, right? So once you have your structures and you can map them properly and you understand what's going on, symbol-wise, you're good to go. And so I always like to work in the target version, so I'm not overcoming challenges that don't exist in the real one or making life harder for myself, but porting those symbols over definitely makes your life easier. Bin diff is open source now. An amazing project for some grad student would be to port bin diff to Ghidra. But yeah, that is definitely good to do if you have the sources to compile it and port your symbols. This does not have a default bin differ, but what it does have is, I think, flirt symbols. Flirt is a database. Oh, it still has it. So Flirt is or was a database of compiled libraries. And so what you could do is say, hey, go through and find all of the functions that you think are statically linked in here or inlined from known libraries. And it would do it for you automatically from their database.
They're doing Lumina.
Lumina?
Yeah, is what it's called.
Okay. Does Ghidra have something like that?
It's paid nice, so I've actually never never used it
There's
myself.
an open version.
Is there?
Yeah, you have to do some like overriding stuff, but someone's running their own server. You know, it's fine.
But yeah, work in both ways. Work statically, work dynamically, use that information to inform back and forth to speed up your understanding. If you're just doing static stuff, you are doing more thinking than you need to, right? If you can get a block run pretty much any time, you say, I don't know what this block is doing, set a breakpoint there, send some input. If it breaks, you can answer a lot of your questions by looking at what piece of the code is looking at what part of your data at the time, right? And then bring that back into your static analysis and really speed it along. So, this is by far the most complicated manipulation that's been done in class so far. It's not simple. It's not obvious why things work the way they do if you don't have a pretty good understanding of that allocator. This is the sort of problem that a normal, modern exploit looks like, right? You don't necessarily get immediate control of anything that's very useful. You get indirect control of something that if you're clever, you can turn into something useful. And so this is a good example of that. It's not a good example of the main problems with the heap, right? This does not deal with the fact that the heap is a dynamic system. We have made the assumption that these two things are concurrent. That's not going to be the case if you have a heap overflow, right? You're not going to know where you are in the heap at any given moment, and that's the big challenge. There are ways to solve that problem, and we'll look at those in subsequent lectures. But this type of deal where you get very simple control of some offset, and then you're like, oh, I'm going to build a whole fake structure for an algorithm to work on, that's very normal, right? And it very often devolves into that, okay, I got to the place I wanted to go to, but now I'm crashing halfway through and I'm not sure why. Okay, now I have to manipulate my input to bypass that, to avoid it, to make sure I'm not crashing. Okay, maybe I need to go back and fix something else up. All that stuff happens in most modern exploits. Whenever you're doing something complicated like fake object creation, that stuff comes up all of the time, right? And the process is, think about the program as a flowchart. Think about where I want to be in the flowchart, what I want to avoid in the flowchart, figure out what determines where I go through the flowchart, label it, and work from there. All right, who needs a beer? All right, we're good, I think. It's been 2 solid hours of looking at disassembly and working with structures and stuff, so. Next class, I will probably go back to the situation where people have the crash here, and we'll walk through using the write what where, and we'll get everybody doing it, because I suspect very few people here have the write what where overwriting something useful, and nobody here actually has it returning out of free. You guys want to continue that on next class? Does that seem useful? Yes. Okay. Does anyone not want to do that?